Yeah, so I'm here to tell you about cosmology. And hang on, why is my thing not working? Maybe I'll do it. And okay, so everyone knows that there's this concordance flat lambda CDM model that we kind of just take for granted. It's the simplest model that is consistent with all of the, most of the observations that we have today. And usually when we talk about this model, we see this represented by this cosmic pi, which essentially shows the composition of the universe today. So we have 70-ish% of the energy density of the present day universe in this lambda CDM model in the form of some mysterious dark energy, and about, there you go. And 25% or so, 23% in the form of a dark matter, which is, I guess a lot of you work on dark matter. This is non-relativistic, cold stuff. And there's a tiny trace amount, 5% or so, of ordinary things that are, ordinary matter like atoms or us, basically. Now, there's actually more in this model than just this pi. So, for example, in this lambda CDM model, there's also a flat spatial geometry that is part of the model. And the initial conditions are consistent with those given by, single field inflation. Yeah. But anyway, so that was one pi. But as you probably recall, I actually showed a second pi on that slide as well, and that is because the composition of the universe and what things are important at what times is something that depends on what time you're looking at the universe. So the pi that we normally see is the one that is for the present day energy density composition. But if we wind back the clock to an earlier time, then things would look rather different. Okay, so we'll just have to wait for the slide to come back up. But when it does, do I have to share screen again? No, I don't. I think it's still being shared. Yep, there we go. And so if we wind back the clock, as I said earlier, if you wind back the clock to 13.4 billion years ago, and the significance of 13.4 billion years is that was actually the time of photon decoupling, the time when the CMB, the 3-degree background was formed. You see that the energy density of the universe was actually quite different. So you had more dark matter then. You also see the neutrinos, the photons, atoms at about 12%, and don't really have dark energy hovering around at that time. Okay. So what I'm going to do today is basically to give you a brief overview, in the next 7 lectures actually, of what's happening in this grand picture that we have come to understand as the hot Big Bang model. And just roughly speaking, the grand lecture plan is that in today's lecture and also tomorrow, I'll just give a really basic introduction to cosmology. I call it Cosmology 101. I'll do it on slides, even though I was told I should do it on Blackboard. But I'm not doing it on slides because I expect you to all know about this stuff anyway, at least to a pretty good extent. So I'm really just kind of telling you this stuff again, just to maybe close a few gaps here and there, okay? So I'll tell you about homogeneous isotropic universe, what we do, how we describe it, and then today and tomorrow I will say a few words about the hot universe, like thermal history, and also some really brief introductory inflationary universe stuff. And then next week, 5 lectures I'll spend on the inhomogeneous universe, and I expect most of you would not have seen too much of that, so I'll do that mostly on the blackboard. At least I'll try, okay? To write things on these blackboards. Okay, cool. So so today's lecture is basically covering how we describe all of this history of the universe, and then tomorrow will be focusing on these aspects of the universe, and inhomogeneous universe next week is basically all low redshift stuff. Okay, are we happy with the grand plan? And then I will now start with Cosmology 101. Okay, so the universe that we live in today, we often call that the Freeman-Lemaitre-Robertson-Walker universe, FLRW, okay? And the basic idea behind that, the first tenet about that is called the cosmological principle. And essentially, the cosmological principle states that our universe is spatially homogeneous, and isotropic on sufficiently large length scales. Another way to express this statement is that we're not special. Okay? Now, homogeneous, there's three keywords: homogeneous, isotropic, and large length scales. Homogeneous and isotropic sound like the same thing, but they're not. Because homogeneous means the same everywhere, whereas isotropic means the same in all directions. Okay, they're slightly different things. So if you look at these three pictures over here, in this first universe here on the left, it's isotropic because it looks the same if you happen to be sitting in this galaxy-like thing, this disk thing there. If you're looking around, all around you, it looks the same in all directions, but clearly it is not homogeneous. Okay. This universe here in the middle is pretty homogeneous because you've got all these nicely spaced planes all flying in one direction, but it's not isotropic because the planes are all going in one direction, so you break isotropy. This one, on the other hand, on the right, it is both homogeneous and isotropic. So when we're doing cosmology, we are basically saying that the universe looks sort of like this on sufficiently large scales. Now, what's sufficiently large scales? We're talking about 100 megaparsec and larger. Okay? Megaparsec is not a unit that you use a lot, so let me just give you an idea of what it is. So 1 parsec, okay, PC, is 3 times 10 to the 18 centimeters. So an enormously large scale, and we're talking about megaparsec, hundreds of megaparsec when we do cosmology, so it's a really large scale. Just to give you an idea, the distance from the Sun to the galactic center is about 10 kiloparsec, so that's not cosmology, in other words. Distance to the Virgo cluster is 20 megaparsec, still not cosmology, okay? The size of the visible universe is of order 10 gigaparsec, okay? So when we do cosmology, we're really looking at 100 megaparsec up to about, say, 10 gigaparsec. Okay, these are the scales we want to describe. Now, okay, homogeneous isotropic sounds like a very easy thing, but do we actually have evidence to back up these assumptions? And well, we do, actually. So this here shows a distribution, the local distribution of galaxies as measured by the 2 mass redshift survey. It's a bit old, but it gives you the idea anyway. So if you look at this, each dot here is a galaxy, and the color coding here gives you the redshift of each galaxy, so how far away they are from us. There's a black band here in the middle, that's basically just the galactic plane. Okay, since we can't really, that's this galactic plane that's blocking our view, we can't see the galaxies behind it, which is why it's black here, okay? But if you just ignore that black band and squint your eyes a little bit, look at this picture, it is pretty homogeneous and isotropic, okay? So that's one piece of support evidence to support the assumption of large-scale homogeneity and isotropy. Also, this is old, as I said, well, not that old, maybe a decade or so. But we also have other ways to support this assumption. So, for example, here is the several pictures of the cosmic microwave background. This is a 3-degree background that's supposed to have been formed in the early universe, and it's redshifted to about 3 degrees Kelvin today. So these are photons, relic photons. And so the green here was basically the first detection by Pensins and Wilson back in '65. They were really engineers playing around with their radio telescopes. And suddenly they saw this background white noise kind of thing in the results. They had no idea what it was. In fact, they were even investigating if it might have been due to white dielectric material, aka bird droppings. And until they talked to cosmologists, they realized that they actually detected something important. Okay? So it was a 3-degree background. They got a Nobel Prize for it, for that measurement in 1978. And there have been several more generations of these microwave background probes since. So in the 90s, we had the NASA COBE satellite that was sent up into space to actually look for fluctuations in the temperature of this background. Okay, so this background is on average about 2.73 degrees. But if you actually look very closely, there are also these 10 to the minus 5 temperature fluctuations. Okay, so these red, well, okay, the red is the galaxy, but if you look at the green and the blue spots here, they are basically a code for how hot the CMB is at that point in space. Okay. That was in the 90s. Those guys got a Nobel Prize as well for their measurement. And in the 2000s, we had the WMAP measurement, which was of a much better resolution. And since 2013 or so, we also have the measurement from the Planck satellite, which is basically the state-of-the-art of the large-scale temperature and polarization fluctuation measurements that we have seen. Okay, so this is this really nice figure that you get that gets shown all the time. You have the Kirby measurement, the W measurement, the Planck measurement, all contrasting the resolution of each measurement. So they've measured the temperature as well as the polarization of this background. Okay, so these are fluctuations, okay, which I'll get onto next week. But the point is that on the whole, if you ignore these 10 to the minus 5 fluctuations, you have pretty good homogeneity and isotropy in the universe as we can see it today. Okay. So, so the FLRW universe is homogeneous and isotropy, and it looks like we do have the observations to back up these claims. So what do we do about it? Well, obviously we want to be able to formulate this in some mathematical framework. And if we have homogeneity and isotropy in the universe, what it means is that my three spaces are maximally symmetric. Okay? In other words, my three spaces should have 3 translational and 3 rotational symmetries. Okay? If I go from this point to a point, I translate, I should see the same thing. Okay? I can translate in the x direction, y direction, z direction. That should always preserve what I see, the homogeneity and isotropy that I see. Rotation as well, okay, I can rotate this way, that way, whichever way. Now, so a space-time geometry that satisfies these requirements of 3 rotational and 3 translational symmetries is the FLRW geometry, which is usually written in this way. Okay, so this is the line element, and there's the time part, which is familiar to you. And then this part here is the space part here is the interesting part. Okay, so what I see here is this thing, A. It's called a scale factor. Okay, and it's a function of time in general. And here, all of this describes the spatial geometry of the universe. Okay, and as you can see, it was written in spherical coordinates. But as you can see here, there's a k parameter, and this parameter here tells you whether you're living in a flat universe, in which case k would be 0, so Euclidean geometry, or you might be living in a hyperbolic space, in which case k would take on the value of -1, or you're living in a spherical space, then k would take on the value of +1. Okay, so these are essentially the characteristics of this FLRW space-time. Now, one thing about the scale factor, it's what the scale factor does essentially is that it describes how the length scales change as the universe expands. Okay, so if I take the scale factor at some time t2, and I divide it through by the scale factor at a different time t1, then this ratio here would tell me how, by what factor, a physical length scale has increased between these 2 times. Okay? And oh, by the way, cosmologists, like relativists, like to use minus, plus, plus, plus. So sorry if you've been doing QFT lately and do plus, minus, minus, minus. Okay. Okay, just to illustrate what these 3 types of spatial geometries are. So this is flat. Okay, just flat sheet. So if you think about time as going in this direction, then each slice of space that you have at each time would be flat. And a negatively curved space would look like this. Okay, so like a saddle point. And then you have this positively curved space, which is kind of spherical. Okay. Now, at this point, I'm going to introduce a few terms. So that will come back again and again. The first is that of a co-moving observer. Okay, so in cosmology, the co-moving observer is very important. And essentially what a co-moving observer is that it is an observer who is at rest with the FLRW spatial coordinates. Okay, so someone who is not moving in R, not moving in theta, not moving in phi, in this space-time here, is a co-moving observer. Okay, so another way to illustrate it is if you imagine that I put in a grid to describe my spatial coordinate system in the FLRW universe, and then I put 4 people sitting here at the grid points. They are the ones that are at rest, and they, as you evolve the system, as you let the universe evolve in time, then they will still be at rest with respect to these grid points that I've drawn. However, the important thing is that A, if it's an expanding universe, A would increase with time, so the physical distance between 2 co-moving observers will increase. Okay, so they are at rest with the coordinate system, these observers, these co-moving observers, but the distance between a pair of co-moving observers will become larger and larger because A is an increasing function of time. Okay, so time goes this way, the scale factor also grows. And, but as said, the coordinate distance between a pair of co-moving observers would remain unchanged. That's why they're co-moving observers. Now, at this point, I'm also going to tell you a bit about geodesics. And if you have no other forces at play other than gravity, which is itself described by GR, then a test particle will move on the geodesics of that space-time. Okay? So in other words, a geodesic is kind of like a generalized straight line. Okay, because we know from Newton's first law, right? Things that you don't apply an external force on will either remain at rest or keep moving in a straight line. Okay, but and to generalize that to a more complicated space-time geometry than just Minkowski, then essentially the generalization is that with the in the absence of external forces, particles move on geodesics. Okay. Just to liken it to something that you probably have experienced, when you look at flight paths on the surface of the Earth, they are more or less geodesics of the surface of the Earth. Okay, so I mean, you have the Earth, which is a sphere, and then which is a sphere, okay, and then you have like the flights that are moving on this curved surface, two-dimensional curved surface. And these flight paths are the geodesic of this curved two-dimensional surface of the Earth, okay? Barring politics and weather patterns and whatever, okay? Of course. Now, why do I bring up geodesics here? I bring up geodesics because if you have particles that are moving on the geodesics of an FLRW universe, then they all suffer cosmological redshift, okay? In other words, if you look at the momentum of a particle, let's say, that is moving on a geodesic, and you ask what is the momentum measured by a co-moving observer, then this momentum would scale like the scale factor raised to the -1. Okay, so here's a graphic to illustrate what's happening. Here's your particle that is moving along in a straight line here in this picture, in this schematic. And observer in the yellow phase would measure the momentum, but at a later time, the particle would have moved over here, and the guy with the green phase would measure a smaller momentum that goes like a to the -1, okay? And so on and so forth. You know, the further down it goes to the red phase person, the momentum will be smaller again, okay? So that's that's cosmological redshift. And it tells you how the momentum of a particle moving on the geodesic of the FLRW universe decreases with expanding space. Okay? It's not energy, by the way, that redshifts. It's momentum. It's always the momentum that redshifts, not the energy. Now, if it helps, another way to think about this, which actually I like a lot, is to think about the whole thing in terms of wavelength. Okay, because we know, well, from quantum mechanics that wavelength, the Broglie wavelength of a particle with lambda is inversely proportional to the momentum. Okay, so what I can do immediately is to think about my expanding universe as if it was like an expanding balloon, and we live on the surface of that universe. And if you draw a wave on it and you let the universe expand, then clearly the wavelength will become longer and longer. So this is actually, I find a rather nice way to think about cosmological redshift. It's really essentially is what's happening. Now, another thing that is commonly used in cosmology is the redshift parameter, which is usually called Z. And essentially, it's a parameter that I guess comes from astronomy, maybe. And what you do here is that you look at the wavelength that is observed by a co-moving observer. That would be lambda O. And you divide that through by the wavelength of a particle that was originally emitted by a co-moving emitter a very, very long time ago. Okay? And since I know that I have lambda is inversely proportional to p, which is itself inversely proportional to the scale factor, what I come up with immediately is that this ratio of the wavelengths would be given by the scale factor at the time it's observed, okay, divided by the scale factor at the time at which the particle was emitted. Okay? It doesn't matter whether it's photons or any other particle. This is true for all particles. And if I assume that this particle is observed today, okay, like right now, then I can parameterize this ratio here in terms of a redshift parameter Z. Okay, so the ratio of the scale factor at the time of observation divided by the scale factor at the time of emission is equal to 1 plus Z, Z being the redshift parameter. Okay? So if I just look at this relation here, what this means is that a particle that was emitted at a very early time t would have been emitted when the scale factor A was very small. Okay? The longer time ago, the smaller the scale factor. But when it is observed today, the redshift parameter would be very large. Okay, so the higher the redshift, the smaller the scale factor, the smaller the time. Okay, so this is indicated by basically this set of arrows over here. And since in an FLRW universe, this kind of mapping is always true, I and most people, most cosmologists would tend to use redshift, time, and scale factor interchangeably as a measure of time. Okay, so large redshift as early time, small scale factor. Let's keep that in mind. Right, so that was geometry. Let's now move on to describe the stuff that is in the universe. Okay, in other words, we want to be able to describe the matter and energy content. Now in GR, when you want to write down the matter energy content, what you do is to write down a stress energy tensor, T mu nu. Okay, and T mu nu is this symmetric, this 4x4 matrix-like thing, which is symmetric under the exchange of the two indices. But if you ask what are these entries physically corresponding to, then essentially the time part of T mu nu gives you the energy density of the stuff. And here in the space part, the space part, you have T11, T22, T33. This is essentially just the pressure of the stuff you're trying to describe. Okay. There are also these other entries here, like energy flux and momentum density. And of course, actually T01 and T10 should be the same because the stress energy tensor is symmetric under the exchange of the indices. But if you want to interpret it, then you could call this energy flux and this is called momentum density. They call different things, but they are the same, really. Then you have in the space part, also in the off-diagonal elements, the shear stresses. So for those of you who have any experience with engineering, shear is basically when you have a surface and then you apply a force in a direction that's parallel. So you end up kind of shearing something. Okay? Pressure is isotropic, shearing is kind of this motion. This kind of force applied on a surface. Okay. Now, that's a general stress energy tensor, and actually next week when we do Inhomogeneous universe, all of these entries will matter. But now, for now, we are looking at homogeneous universe and isotropic as well. So it turns out that the stress energy tensor will simplify significantly. And essentially, in an FRW universe, there's only one viable form for the stress energy tensor, and it looks like this. Okay? So you have the energy density up here, rho, which is the energy per unit volume of some substance alpha in its rest frame. Okay? And then here in the diagonal entry, you have the pressure of the stuff. Okay? And you write down, so I have this little label here, alpha. And that is because you could have multiple kinds of stuff in the universe where each has its own pressure and energy density. So, you may have photons, which would have its own stress energy tensor, and dark matter, you'll write down one for dark matter as well. So the alpha labels the kind of stuff, different kinds of stuff that you might have. Okay? Now, obviously there are no off-diagonal elements, because as soon as you have an off-diagonal element, you will break isotropy of the universe. Okay, so for this reason, they're all zero. And also, if you look at the dependence of those finite non-zero entries in the stress energy tensor, what you see is that these, like rho and p are only allowed to depend on time, but not on the spatial coordinates. Again, it is because we have demanded that the FRW universe is homogeneous and isotropic. Okay? So this is the only thing you can do, give them a time dependence. Now, the next question then is, how do these quantities evolve with time? Well, to do that, what we can do is to, again, appeal to standard things within general relativity. And what we can do is to basically apply local conservation of energy momentum. Okay, so in GR language, this is basically just a covariant derivative of the stress energy tensor, and you make that equal to zero. Okay, well, it has to be equal to zero. That's a continuity equation that would pop out in the end. Looks like this. Okay, so it's an equation of motion for the energy density of substance alpha. And what you see here is that it depends on what the scale factor is doing. So you have A dot divided by A over here. And then over here, again, you see energy density and the pressure, and all of that is equal to zero. Okay, so this is just a consequence of that, of this standard conservation law. You would write down a continuity equation for each substance alpha. That's not entirely true, actually, because you could have two kinds of substances that are coupled together and they're exchanging energy. Then you write down one continuity equation for this combined system. But in general, every time you have one system, one substance or maybe two substances that are kind of coupled together and isolated from everything else, you would write down a continuity equation for that. Okay. Now, this is only one equation for the energy density, rho. I still have pressure here, and I don't have an equation of motion for that. Now, you can ask, can I write down an equation of motion for P as well? And the answer is, yes, you can. You can actually play around with this local conservation of energy momentum and try to get an equation for P as well. But the problem is that that equation will not be linearly independent from what we have over here already, rho, and then some other equations as well. So in the end, what it means is that the continuity equation here does not completely specify the evolution of rho and P. Okay? In fact, what we need to do is to, in addition, specify a relation between rho and P ourselves. Okay? Which is not surprising because, if I want to describe some stuff, okay, and I don't know what that, Einstein's equation doesn't tell you what that stuff is. Okay? You have to specify what stuff you're trying to describe. Okay? And the relation between rho and P is essentially the equation of state of that stuff that you're trying to describe. Okay? And that's a property of the substance. So we need to put that in as an external input. Now, there's a common way to express this equation of state, and it's called the equation of state parameter W. And W is essentially just the pressure divided by the energy density. Okay? So W can be a function of time, or it could be constant. It depends entirely on what you're trying to describe. Okay, so you could be trying to describe dark matter, it would have its own W, or you could be trying to describe photons, which would have a different W. But anyway, if I take this expression here, W is equal to P divided by rho, and if I just make the assumption that W is a constant in time, then what I can do very easily is to put this relation back into the continuity equation. Okay, so I have rho here, I have a P, but if I see P, I substitute it for W times rho. Okay, then in that case, this equation is very easy to solve analytically. And in fact, it looks like this. If you assume a constant W, rho would look like this. It would go like the scale factor raised to the minus 3, 1 plus the equational state of the stuff you're trying to describe. Okay, and so this relation here, this expression here tells you how the energy density of the substance alpha would evolve with the scale factor. Okay? And as said, W alpha is something you specify. Now, let's think about what kind of stuff we could possibly have in the universe. Well, you could invent stuff, whatever stuff you like, but some generic things that we could have would be non-relativistic stuff. Okay, so things like atoms or, I don't know, molecules, whatever, tables. And that's non-relativistic because they're not moving at the speed of light. And of course, dark matter, which, as we all know, does not emit light but feels gravity. GR people usually call it dust. Doesn't matter what you call it. The bottom line is that these things are non-relativistic. Okay? If you have a non-relativistic substance, then the energy of that substance will be dominated by the rest mass of that substance, and it doesn't have much kinetic energy relative to rest mass energy. And what is pressure? Pressure is really just kinetic energy. Okay? Think back to first year thermodynamics. You know, they tell you about how you calculate pressure and temperature and all that. It's basically all about molecules flying around in the box. So pressure is just kinetic energy and essentially. Okay? I mean, in the ideal gas case anyway, you could, of course, also have forces at play. But anyway, in the ideal gas case, it's just kinetic energy. So if I don't have much kinetic energy versus rest mass energy, then what it means is that the pressure would be small relative to the energy density. So P is much less than rho. In which case, the equational state parameter would evaluate to something very close to 0. Okay? So if I now stick this in, Wm, stick it back into the equation from the expression from the previous slide for rho, what I find immediately is that rho m, matter, would go like a to the minus 3. Okay, so that's how non-relativistic energy density evolves with the scale factor. It goes like a to the minus 3, which is actually completely intuitive, I would say, because if you think about something which is just sitting there, not doing much, it's not being destroyed, it's not being created, then the only thing that can affect the way the energy density evolves is the fact that volume is expanding, because the universe is expanding. Okay? And therefore, you have this a to the minus 3 factor, which is entirely due to the fact that volume is expanding. Okay? Now, so that's non-relativistic stuff. What about things that are ultra-relativistic? Well, we should expect a lot of those around as well, because for one thing, we know we have the cosmic microwave background, which is photons, okay? And so ultra-relativistic. We also have a relic neutrino background that is kind of analogous to the CMB, except that in that case, we're talking about light neutrinos forming this background. Okay. Gravitational waves, we probably also had gravitational waves from inflation or wherever, and that would also be an ultra-relativistic kind of substance. Now, if you have ultra-relativistic stuff, then the pressure would be very large, of course. And from thermodynamics, we know that the equation the ratio between P and rho would be 1/3. Okay? So if I now take 1/3 and put it back into the expression from the previous slide and evaluate it, what I find is that rho in radiation goes like a to the minus 4. Okay, so relative to the non-relativistic kind of energy density, what we see here in the relativistic case is that you've picked up another factor of a to the minus 1. And physically, what it means essentially is that you have one factor of a to the minus 3 due to the volume expansion of the universe. And then you have another factor of a to the minus 1, which essentially comes from the fact that momentum redshifts. Okay, so we talked about that several slides ago. Momentum of a particle as it moves along has to decrease with expanding space. Okay, so that's reflected here in the a to the minus 4 for the energy density. Last but not least, you could have funny things around as well. So one famous funny thing is the cosmological constant, okay, which is in modern times more commonly interpreted as a kind of vacuum energy. So basically the energy associated with the fact that you have a vacuum, we have space, all right? This kind of stuff is weird because the equation of state parameter of that is -1, all right? And essentially what it means is that, if you plug this back into the expression up here, is that you have 1 minus 1 the exponent, and so rho lambda is actually a constant in time. Okay, so in other words, the more space you have, the more energy you get. So that's the vacuum energy. Okay, so that's basically the three kinds of things that you see in the lambda CDM model: ultra-relativistic stuff, non-relativistic stuff, and funny stuff in the form of a cosmological constant. You could have other things, of course. The W's will be different. And that's, of course, something you can test against data for. Okay, so that's a picture of vacuum energy, but we don't want to see that. Right. Oops, what happened? Did my animation kill the projection again? Sorry. I should avoid animations. Right, here we are again. Okay. So, now, having written down these three forms of energy density in the lambda CDM model, what we can then ask is, how do these things, how do they compare? How do these different forms of energy compare at different times during the history of the universe? So what you see immediately is that if you take A, the scale factor, to 0, so if you go back in time to the very early universe, you always have the radiation energy density dominating over everything else, because this one goes by a to the minus 4. So if A is sufficiently close to 0, this one here, rho r, is the one that would blow up, okay, relative to rho m, and definitely relative to the rho lambda here, which is constant. Okay, so you have a prediction here that rho r must dominate over rho m and rho lambda. And similarly, you can look at the other end, the other extreme. You take the scale factor to infinity. Okay? So the first thing that would die off when you take the scale factor in infinity is the radiation energy density. Okay? That dies off the most quickly, followed by the matter density. And rho lambda here is the constant, so it's just going to remain. Okay? So what I can do then is to take these predictions and then plot them. And this is what we get. So here, in the horizontal, I have log A. So the log of the scale factor. And I'm plotting here in the vertical the log of the energy density. The green line is the dark energy, vacuum energy. It's the constant, so it's just going to keep going on like this forever at maintaining the same value. And as said earlier, radiation energy density is the one that dominates at early times, so you have the red line that goes this way. And the matter energy density is the one that's kind of intermediate. It's not dominating at early times and also not dominating at late times, but you could engineer things in such a way so that they dominate for a little bit here in the intermediate region. And we have names for these various regimes. So here at early times where the radiation energy density dominates, it's called radiation domination. And here where the blue line here makes an appearance is called matter domination. And when we go all the way here to very late times, the green line takes over, and that will be lambda domination. We also have names for where the red line and the blue line cross. That's matter radiation equality. And similarly, this spot here is matter lambda equality. Okay, so that's a generic prediction for what you should expect to see. I can also actually just take the lambda CDM model as we know it today, with 72% dark energy, dark matter is 23%, etc., and then try to demarcate, the horizontal axis. So here, where it says 0, log of A is equal to 0, is where we are today. And by the way, by convention, the scale factor is equal to 1, set to be 1 today. It's just a convention. You could call it anything, but 1 is convenient, so we call it 1, which is why you have log of 0 corresponding to today. And matter lambda equality was actually something that was not too long ago. It was sitting somewhere here, maybe at a redshift of about 0.5 or so. Okay, pretty recent in terms of, if you think in terms of scale factor anyway. And if you go back, matter radiation equality is around here at about 10 to minus 4 in scale factor, and so on. And just to also give you an idea of where all the major events took place, structure formation, so how galaxies and things come into being, that would have taken place here in the matter domination period. The last scattering surface, which we now see as the cosmic microwave background, was essentially at a time a little bit after matter radiation equality. Okay? And nuclear synthesis would be way back up here, and anything that concerns baryogenesis and dark matter formation, etc., would have been way earlier than anything I'm showing on this plot during radiation domination. Okay. Well, okay, conventionally anyway, you could have, of course, early matter domination if you like, but this is the standard picture. Okay, and just going back to the energy pies that we looked at earlier. And as I mentioned earlier, the pies look quite different depending on where you look at the energy composition of the universe. And at earlier times, you have mostly dark matter and no dark energy. That is all because these different forms of energy densities evolve in different ways. Okay, and therefore, during matter domination, you'll obviously see more matter being the dominant component of the energy budget of the universe. Okay, right. Now, one more equation that I need to introduce is that of the Freeman equation. So far we looked at, rho, the energy densities, and how they scale with the scale factor, but I haven't said anything yet about how the scale factor itself evolves with time. Okay. And to find out how the scale factor evolves with time, what we need to do is to solve the Freeman equation, okay, which usually takes this form. So it's actually an equation for the time derivative of the scale factor, so A dot divided by A, and squared. And this thing here is usually called the Hubble parameter, H. Okay, so A dot divided by A is called a Hubble parameter, H. And this equation here is proportional, this H square here is proportional to rho. Okay, so rho is the energy density that we talked about just a few slides ago. And you've got to sum up all the different kinds of energy densities that we have. You have radiation, if you have matter, you have weird stuff, you stick them all in here, into this sum, and add them all up. Okay, there's a proportionality factor over here, G. Okay, and G is the gravitational constant, which must be there, of course, because we are looking at gravitational effects. Now, there's one more term over here, which is outside of the sum, by the way. I'm sorry about the way I've written this, not very clear, but okay, there's a sum and then an a pi g, this is separate. Minus k divided by a squared, okay? That's the part, that's the term that comes from curvature, okay? And if you recall, the curvature parameter could be 0, in which case you're living in a flat space. It could be +1 or -1, okay, for any kind of curved space that you have. The Freeman equation itself is a consequence of the Einstein equation. So basically what you do, if you really want to try to do that exercise, is to take the Freeman-Lemaitre-Robertson-Walker metric, compute your Christoffel symbols, compute your Ricci scale, your Riemann tensor, compute your Ricci scalar and your tensor, stick it all in, and take the T mu nu of the form that I showed you earlier with the diagonal entries. After about, I don't know, maybe 3 pages of work, you'll get to this point. Okay? You might want to try it once for the fun of it. Now, that's one way to write the Freeman equation, but you've probably also seen the Freeman equation written in a slightly more usable form, and it looks like this. Okay, so you have again x squared of t on the left-hand side, but on the right-hand side here, I have rewritten things in this funny way. Okay, so first of all, I have this factor x squared t naught, which is essentially the Hubble parameter again, but evaluated at the present time. Okay, so t naught is the present time. And all the energy densities that were previously in the sum, in this sum over here, has been absorbed into these reduced energy density parameters. Okay, so so omega m here is basically the energy density in non-relativistic matter, and then you divide it through by what is called the critical density. Okay, and the critical density essentially absorbs all the cosmological, the gravitational constant, etc. Okay, so you have a reduced energy density parameter for each kinds of substance that you have. And for matter, you have this a to the minus 3 scaling. For radiation, you have an a to the minus 4 scaling. Omega lambda here is the vacuum energy, so that's a constant that doesn't evolve with time, as expected. And last but not least, it's also common to reinterpret the curvature parameter k as a kind of energy density as well. So omega k here is just defined as minus the same curvature parameter we saw earlier, divided by the Hubble parameter today. Okay, and it has a scaling to a to the minus 2, which actually just came from the Freeman equation, which we saw earlier anyway. So okay, it's just the same a to the minus 2. Okay. Now, if we were living in a flat universe, then omega k would obviously be 0. In which case, if you sum up everything else, then you will have omega m plus omega r plus omega lambda being equal to 1. Okay. Normally, you only see omega m plus omega lambda is equal to 1 if you look into the cosmology literature, and that is because from measuring the C and B temperature, we know that this is a 3-degree background, and we also have a perfect Planck spectrum from that measurement. And if you put the 3 degree Kelvin into a Planck spectrum and try to calculate what is the omega r, then it turns out to be a tiny number, 10 to the minus 5. Okay? So relative to 0.7 for omega lambda and 0.3 for matter, this is negligible. So that's why you don't usually see omega r being mentioned in this relation. Okay? So as said, that's basically the current measurements we have at the moment. Omega m is about 0.3, lambda about 0.7. The curvature parameter omega k is highly constrained to be less than about %, and h naught is of order 70 kilometers per second per megaparsec, but the precise number depends on who you ask, okay, and which set of measurements you believe in. Now the picture illustrating like a generic idea about what we expect the universe to do. So our universe is this one, the red line, which has omega m or 0.3 and 0.7, and what I'm plotting here is time in billions of years, and over here is the scale factor essentially, okay, relative to the scale factor today. So what you see in the red line is that you have a lot small scale factor, and then it increases and it keeps on increasing. Okay, so it's going to just keep growing forever if the universe is indeed composed of cosmological constant and other, more regular stuff like dark matter, for example. Here's another example, the yellow line. This one here is corresponds to a closed curved universe, k of +1. And if you look at the omega m here, it has an omega m of 5 and no dark energy. So this universe here collapses on itself again. Okay, so it doesn't, because it doesn't have the dark energy to keep it expanding. Now, so that's the Freeman equation. You probably have also seen the Freeman equation written in yet another form, which looks like this. And actually, this particular form of writing the Freeman equation, which you can actually try to derive by combining the usual Freeman equation from 2 slides ago with the continuity equation from about 10 slides ago. If you combine them together, do a bit of algebra, you can actually massage it into this form. Now, what's nice about writing a Freeman equation in this form is that here, what you see is an explicit expression for the acceleration of the scale factor. Okay, so you have 8 double dot here divided by A. Okay, Freeman equation as usual is just 8 dot. Here is 8 double dot. Now it's nice because this tells you what conditions would give rise to an accelerated expansion. Okay, and you see here on the right hand side what conditions needs to be achieved. So when I show this, people usually ask me what happens to the curvature parameter k. Did I just drop it? I didn't. It just drops out by itself. Okay, so it doesn't make a feature here. It's just like this. So I have -4 pi g divided by 3, and then the sum over all the energy densities plus 3 times the pressure. All right? And so immediately what you can see is that you could have accelerated expansion depending if the sum here evaluates to something that is less than 0. Okay? If the sum is less than 0, I have a minus sign in front, then all of the right-hand side would be larger than 0, in which case A double dot will be positive. And in order for that to happen, I need the effective equation of state parameter of the universe, which is just the sum of the pressure of all the stuff, divided by the sum of the energy densities of all the stuff. And I need this thing to be less than -1/3. And when that's achieved, we have accelerated expansion. Similarly, if my sum here, energy sum, pressure sum, evaluates to a positive number, then everything on the right-hand side would be negative, and then I will have decelerated expansion. Okay? And the condition to achieve that is that the equation of state, the effective equation of state of the stuff in the universe is larger than -1/3. Okay? So what this tells you immediately is that if you only have matter in the universe, you're not going to have accelerated expansion. You will also not have accelerated expansion if you have radiation. Okay, you really need something rather weird for accelerated expansion to happen. And a cosmological constant will do it. Dynamical dark energy driven by a scalar field will do it. But that's the condition you need for the accelerated expansion to happen. Right, so last section before I will be told to stop. But I hope everyone is okay with the first an hour or so. Are there questions or anything? No? I guess you know it all anyway, right? So let me just say a few words about distances and horizons and things, okay? Now, so previously I wrote the FLRW metric in this way, okay? It's actually potentially not the most intuitive way to write that metric, because actually what you can also do is to define a parameter called chi. Okay? And essentially you just call all of this stuff here dr squared 1 minus kr squared, and just redefine that thing and call it chi, d chi squared. Okay? The advantage of doing that is that you will have rather different solutions once you put in different values of k. So you will have chi is equal to r if k is equal to 0, which is obvious. And if my k is hyperbolic, then you naturally end up with chi is being to the arc hyperbolic sine of r. So the word hyperbolic is even in the function, which is good. And then similarly, if k is equal to +1, then chi will evaluate to something that is like this arc sine r. So this is a spherical geometry. Now, I can also do another thing to make things a bit nicer to work with. And in fact, in the inhomogeneous part of this course, I will be using this conformal time parameter quite often. And essentially what you're doing is that you say, well, you know, I look at my metric, I've got the scale factor in here, but there's no scale factor in front of time. It looks kind of uneven. So what you do is to define a conformal time so that you can just basically factor out this whole scale factor in front to make it the thing look conformal. Okay? So then you're left with something like this. You have a scale factor out here, and eta here, it will come back again. Eta is time, okay? Just keep it in your mind. Eta is time. And then you have minus d eta square, which is the conformal time, as said. And then the dr square in my new coordinate system becomes d chi square. And all of the stuff here multiplied in a solid angle is sine h square for k of -1, chi square for k of 0, and sine square chi for k of +1. Okay, so these are the three different cases for three different types of geometry trace. Now, so from now on, I'm going to write my, at least for now, I'm going to write my FRW metric in this form. Now, at this point, having rewritten my metric, I'm going to introduce the concept of a co-moving distance. And let's think about a radial light ray. Okay? So a radial light ray is essentially a light ray that is moving forward in time, but not moving in the theta direction or in the phi direction. It is only moving in the chi direction. Okay? In which case, what I can immediately do to figure out what this light ray is going to do is to take my line element. Okay? Take my line element from previous slide over here. And it's a light ray, right, I said. So it's light-like, and therefore ds squared has to be equal to 0. Okay? So I set that to 0, ds squared is equal to 0, and I only take the conformal time here and the d chi squared because it's a radial light ray that doesn't move in theta and phi. Okay? So I end up with a thing like this. Like this. That's good, because then, having written this down to describe the trajectory of a radial light ray, I can immediately rearrange it to solve for chi. Okay, so this thing here, chi, is called a co-moving distance, and it is essentially just the conformal time at the time of observation minus the conformal time at the time of emission. Okay, so all I've done is to rearrange this thing. Okay, like d chi is equal to the eta. Okay, and then I do and then I integrate. That's all I've done. Okay. So then I end up with this nice little integral relating. So I have a dt there because dt is equal to a conformal time, d conformal time. And there's one more trick I can do to massage this integral here into this form, which contains a Hubble parameter. Okay, and that's basically just using the Freeman equation. So I mean, maybe I'll just do it since I'm here. So I have c dt a. And what I can immediately do is I can factor out the, okay, if I'm in natural units, I don't have the c anyway, and I rewrite this in terms of the scale factor, okay, and then what I have to do next is to look at, I can rewrite it again in terms of redshift, so I have dz, dA, and then dA, A, dt, dA, and dz, dA, and then I will have an a square here. Hang on, what am I doing? Something doesn't look quite right. Hang on, too many a's, do I not? No. dz. What am I doing? Something is not quite right. I have a t, no, and then dz, and then dz, d. I'm really bad at this. What did I do? Well, anyway, whatever. Maybe I won't do it because I'm just, I'm like stuck and I didn't have my notes there and I'm really bad at doing things on the spot. But anyway, once you, I'll figure that out if you want to see it. Anyway, in the end, if you put in the Freeman equation, you will eventually end up with dA dt and then a squared, a over here, which is what gives rise to this h that is down here. Okay, and then you rewrite it in terms of dz. And then you have this nice integral over redshift that you integrate from the time of observation to the time of emission. Okay? Now, okay, so we have this. We have the co-moving distance, which is given by this expression that I saw earlier. And as said, it's basically just the co-moving distance, just a coordinate distance that is traveled by a light ray between the time of emission and the time of observation at z of 0. So what we can do then is to try to plot it. And so here's a nice plot that I stole from Daniel Bauman's lecture notes. And we are here sitting up here, okay? And here in the horizontal, what we are plotting is the redshift, but there's also a different scale here, which is the co-moving distance. And each of these lines over here, this solid line here, is basically the trajectory of a light ray from some early time. Okay, so this is early time, CMB times. It moves towards us, and as it moves towards us, the conformal time also increases, as it should, because time's moving forward. And then you are also moving in space. Okay, so your co-moving distance is also increasing as you as you move forward. Okay, and so that's this picture. Now, having defined a co-moving distance, there's actually one more thing we can look at, and that is we can take the emission redshift to something very early in time. Okay, in other words, I can take the emission redshift out to infinity. Okay, so the very, very early universe. Then what you get essentially from this integral is what is called a co-moving particle horizon. Okay, so that's basically the maximum distance that is possibly covered by light. Okay, since the beginning of time. That's the horizon. That's a particle horizon. Okay. Now that's just a definition, but there's one more thing that's of interest, and that is, okay, so you have the trajectory of the light ray over here, right? And that's the co-moving distance that's covered in some conformal time. Now, there's also a mapping that is kind of implicit here, and that is the further back you move back in time, the higher the redshift. Okay? And there is a mapping between the co-moving distance that the light ray moves and the redshift that it has traversed. Okay? And this mapping between chi and z depends on h, as we see over here. Okay? I mean, there's chi over here, there's z over there, emission redshift, and the mapping depends on what h of z you put into this expression. So what this means immediately is that if you can somehow measure the co-moving distance chi and also measure z, then what you can do is to get the series of chi versus z and then build a ladder, okay, of chi versus z. And when you do that, what you will have is basically an idea about how the Hubble parameter evolves with redshift, okay, between emission and observation. Now, so that's basically the idea of how we figure out, the cosmic pi and, h of z, etc. So how do we do these measurements? So first of all, measuring redshift is something that astronomers do, and you can do photometry, you can do spectroscopy, and essentially spectroscopy is if you look at an emitting star and then you look at the spectrum of emission. So your emission lines come from, I don't know, hydrogen or light element. Okay, the emission spectrum of these elements are well predicted in the laboratory, so you can just look for these lines in the emission spectrum of your emitting object and then figure out how far these lines have shifted. Okay, so that's spectroscopy when it comes to measuring redshift. Photometry is a rougher method of measuring things, and basically you just look at many, many different stars or galaxies, and then you say, well, those galaxies that are sitting at ratio 10 tend to have a reddish kind of spectrum. Okay, so what you do then in your observation is to use a set of filters and then look at how much power you have in each filter and try to deduce what the redshift would be. That kind of measurement usually is rather error-bar, so it's not used for precision measurements of the redshift. Okay? So spectroscopy is the way to go. You look at the frequency shift of the absorption or emission lines of known atomic spectra from distant objects. Okay? I'm not an astronomer, so I can't really say more about redshift measurements beyond this. As said earlier, to determine what is actually said, we also need a distance measurement. Okay? So in cosmology, there are several ways to do distance measurements. So one of them is called a standard ruler. And essentially the idea here is that you look at an object whose physical size you know. Okay? Call that D. When I take out my telescope to measure the object, I can't measure the physical size, right? I can only see something that subtends some angle theta in the sky. So what I can do, therefore, is to calculate the angular diameter distance of this object, okay, d of A, by taking the physical size of the object that I know, okay, from some means, and divide it through by the angle that it subtends in the sky. This thing is called the angular diameter distance. Now, why is this useful? It is useful because this thing is also calculable from theory. And in an FLRW universe, when you actually sit down and do maybe a page of calculation or so, what you find is that this angular diameter distance is essentially just these hyperbolic sine factors, depending on what geometry you have, multiplied by the scale factor at which the object is sitting. Okay? So your co-moving distance is chi, and A times chi would be your angular diameter distance if you're in a flat universe. And if you're in a non-flat universe, you've got to do a little bit extra work to your chi to turn it into an angular diameter distance. Okay? Now, it's calculable, as said, so what you can do is to take a look at an object whose size you know, or you think you know, and then you measure the redshift of that object, ask your astronomer friends to help with that, and then you have basically 1 point of chi versus z. And if you do it multiple times at different redshift, you will have a nice ladder. Okay? So this kind of measurement is called basically using a standard ruler. Okay? Non-physical size standard ruler. That's one way to do things. Another way to do things is to make use of what is called a standard candle. And the idea is kind of similar, except that this time we are looking at objects whose luminosity we know, or qualify it, we think we know. Okay? So you know, for example, you have an exploding supernova 1A. You have a good theory for what the supernova 1A does. You think you know the luminosity. That's your L. Okay? And we're here on Earth, we can measure the flux of that emission. Okay? That would, if you're looking at a supernova, you would be essentially looking at the magnitude of that object. So what you can do then, once you know L and can measure F, is to compute the luminosity distance, dL. And this thing here is the luminosity divided by 4 times the flux that you measure. Okay? And then square root. Now again, you can predict this luminosity distance from theory. And in an FLRW universe, you have dL being given by, again, this vector of how you deal with your co-moving distance chi, and then you have to multiply this by 1 on A. So if you compare this expression for dL and the previous expression for dA, they look kind of similar, but for the fact that you have this A here and then 1 on A in the other expression. So they are very similar concepts, but slightly different. Okay, which is actually useful because it means that when you are trying to do measurements, you have slightly different parameter dependencies, and which would allow you to break degeneracies. Just to give you an idea of what standard rulers and standard candles we have out there, standard candle is probably something that was has been known for a long time, and the primary standard candle we have out there at the moment is the Type 1a supernovae. These are basically binary systems, and you have a white dwarf as part of the binary, and the evolution of the system is such that at some point the binary dwarf will eat this binary partner and then causes a supernova explosion. So that's a Type 1a supernova, and some people like to think we know how that works very well, and therefore have a known luminosity L. We can measure the flux and therefore compute the luminosity distance that way. Standard ruler is probably a bit more recent in some sense, and one particularly nice standard ruler is that of the acoustic peaks in the CMB. Okay, so I'll get to that next week of where these acoustic peaks come from. But essentially, if you look at the cosmic microwave background fluctuations, there are some nice features in there if you actually analyze the clustering statistics of the little dots here. Okay, so one particularly famous way to analyze the spectrum is to calculate the what's called the autocorrelation power spectrum. So this one I'm sure you've seen, and these oscillatory things here are called acoustic peaks, which has to do with how sound waves propagate in the primordial plasma. And this one particular peak here, the first peak here, has been measured extremely well. The position of that peak is known to about 0.1% accuracy or so. And we also have a very good early universe theory to describe where it should be. So this is normally taken in modern day times as a known physical scale in the early universe. Okay, so the location of this peak serves as my D here for the standard ruler. And again, we know what it looks like, what angle is subtends in the sky. Okay, that's theta. So I can take D divided by theta. That gives me the angular diameter distance to the last scattering surface. There's an equivalent signature of this acoustic peak also in the large-scale clustering of matter. And it's called the baryon acoustic oscillations that was first measured back in 2005 by, I think it's SDSS. And again, you see this little lump here, which is the equivalent of this peak, except that in the first peak here, this one here is in the CMB. This second peak here is a peak in the matter that is clustering, okay, in galaxy clustering. And it has to do with the fact that the propagation of sound waves in the early universe comes from this kind of acoustic oscillations in the coupled baryon and photon fluid. So whatever happens in the photon fluid is also translated to the matter later times, which I'll get to next week again. Okay, there's one more thing I want to just mention very quickly, and that is the idea of using gravitational waves to measure distances. And they're called standard sirens. And essentially the idea here is that you're looking at the in-spiral phase of a compact binary system. So two black holes, for example, and they will at some point spiral around each other. And the thing is that this system here, you can measure the frequency, gravitational wave frequency, okay? And that frequency that measurement allows you to determine what is called a chirp mass, okay? And which is basically given by the masses of the binary system. And from here, what you can do is to calculate the power of the gravitational wave emission. Okay, so once you know the power, which is the same as luminosity, you can treat this system here essentially like a standard candle. Okay, they're called standard sirens, but the background idea is really just that of the standard candle. Okay. The advantage of it is that you have a way to measure the luminosity of the emitting object, which is not quite true if you're looking at a supernova, 1A supernova, where the white dwarf system is not really calibrated. So this one here is at least calibrated to an extent. Okay, so, and if I now take all these distances, measures and combine, if I combine the standard ruler measurements from CMB, BAO, as well as the standard candle measurements from the supernova 1A, then it turns out that they all prefer slightly different regions of parameter space if I fit a model with omega lambda, a free omega lambda and a free omega m. So CMB is here, BAO is there, and supernova is here. And the great thing about this is that once you combine them all together, you essentially single out this point over here, which corresponds to a lambda, omega lambda of 0.7 and omega m of 0.3. Okay? So you add them up together, you have an omega m plus omega lambda, which is essentially 1. And that's really how the lambda CDM model came about. Okay, so you have these different distance measurements that kind of conspire to give you this point here in the middle, which is the best fit for everyone, which is a good fit for everyone. Okay? In fact, you can combine any of these two. If you don't like the supernova data, and a lot of people don't, you can combine BAO and CMB, you still end up here in the middle. Right, and I think the next thing is the last slide I will show, since we are on the subject of distances. So this concept I'm going to introduce here is that a Hubble length. It's not so relevant now, it'll be more relevant next week. But essentially, it's basically just hey, this is not working anymore. Hubble length is essentially just the inverse of the Hubble parameter. And then I have the C there for units, essentially. And actually, there's also this curly H that I've introduced. And the curly H is just the scale factor multiplied by the regular Hubble parameter. Okay? Now, that will pop up more often later on, and we use the curly H a lot in cosmology because we like to work in conformal time. So this curly H here is essentially a kind of conformal or co-moving, if you like, a Hubble parameter. Now, what's the significance about that? The significance of this Hubble length here is that if you look at the Hubble time, which is h to the minus 1, it's essentially a time scale over which the universe would expand by a factor of, say, 2 or so. Okay? So roughly speaking, what this length scale means, or time scale means, is that any two events that are separated by one co-moving Hubble length in space, or less than that Hubble length, can influence each other essentially instantaneously. Okay, two things that are separated too far apart can't influence each other. Okay, so that's essentially the idea of introducing the Hubble co-moving Hubble length at this point. We'll come back later on and say more about this. Just to also highlight, sometimes people call this L of H here, the Hubble, LH here, the Hubble horizon, but strictly speaking, it is not a horizon. Okay? It's just an instantaneous time scale that you look at and you ask, can two events influence each other at that time? It's strictly not a horizon, but in common usage, we keep calling it a Hubble horizon. It's really bad, but everyone does it. I do it too. So yeah, just be cautious about that. So that's all I have to say today, and I'll just leave you here with a brief summary of what you should take away, and if you have questions, please ask.
Questions for Yvonne?
Yeah.
So, I often see that this concept of age of the universe, but when the scale factor becomes really, really small, or like if you go back toward the Big Bang, basically the general relativity kind of breaks down, right? And I was wondering if this like age of the universe as a concept is like valid.
Well, of course, if the age of the universe that people will talk about is really just assuming matter domination, radiation domination. And as soon as you do anything funny, early times, for example, add an inflationary phase, that would already completely break down that idea. So when we talk about the age of the universe, we are really always just sticking with a very standard kind of hot Big Bang without tagging on the inflationary phase. Yes, just standard radiation domination, standard matter domination, and lambda domination at later times, and then you just calculate what is the time since, yeah.